So, welcome all. Myself Diptiranjan Patnaik, and I am assistant professor in the Department of Electronics and Communication Engineering at GL Bajaj Institute of Technology and Management, Greater Noida. Today we will see, and I think we will continue the digital modulation technique, which we have already studied in the previous two lectures. Herein we will study about the BPSK, that is binary phase shift keying. Before that we have studied about the BASK, that is binary amplitude shift keying, then your BFSK, that is binary frequency shift keying, and in that cases we have analyzed the transmitter section and the receiver sections. Then we have calculated about the probability of error occurrence in the BASK and BFSK individually, and then we have seen about the plots using the Gaussian waves. Now we will see another type of modulation technique. This is nothing but the BPSK, that is we will change the phase of the carrier signal. We have already know that in any modulation technique, that is modulation is nothing but the changing of the characteristics. So we can change the characteristics of the signal by in terms of amplitude or in terms of frequency or in terms of phase. So now we will see about the phase of the carrier signal, that is that phase of the carrier signal varies with respect to input data stream or digital data bit. So while changing the phase of the carrier signal, here our frequency and amplitude are kept constant. Okay. So here binary phase shift keying, that is nothing but binary means 2. Okay, that is phase shift, that is another word is phase. So we have binary and that is 2, and that is PSK, that is 2 phases are mainly the 2 phases are represented here, and that 2 phases are represented for 2 different binary digits, that is either 1 or 0. Okay. So here we can see that this is the digital input binary digits, this is binary digit. Okay. So it's we have binary digit 0 0 1 1 0 1 0 0 1 and 0. So for phase modulation we can see that this is the output waveform, that is your 0 is there is no phase change, and there is again 0, again the bit is coming 0. So again that phase is continuous and it is not changing. Okay, this phase is continuous, it is not changing, but when this bit is transition from 0 to 1, at that time what will happen, that phase will also change, that is 180-degree phase shift. That this much again after this interval, this bit is making itself a phase reversal. Okay. Then we can see for 1 1 there is no phase shift change. Okay. Then when 1 is transited to 0, again phase is shifting, this phase is shifting, again 0 1, this phase is shifting. So wherever the bits are changing, that means 1 to 0 or 0 to 1 it is happening, at that time that phase reversal occurs. Okay. And you can see that if zeros are continuous zeros are coming, there is no phase reverse. If continuous ones are coming, there is no phase reverse. Okay, that is, this is your BPSK waveform. Now we have already seen in case of BASK and BFSK how to calculate the symbols. Okay. For symbols like 1 and 0, and in the case of BASK what is the symbol, in the case of BFSK what is the symbols. Now we will see what is the symbol when we are using BPSK, that is binary PSK. So we are using here symbol sorry, symbol 1 and symbol 0. They are transmitted as S1T. Okay, that S1T is nothing but, our two symbols are S1T. S1T is nothing but root of 2EB divided by TB cos 2 pi FCT plus 0 degree phase shift. This is 0 degree phase shift. Okay. Similarly, if I will add 0 degree phase shift, that will cos theta plus 0 degree, that is nothing but your cos theta, and this will happen in the interval t, in the interval 0 to capital TB. Okay. Similarly, S2T, another symbol is your root EB divided by TB cos 2 pi FCT plus 180 degree. So how we can distinguish this 1 and 0? By shifting the phase by 0 degree and 180 degree. So we can see that cos anything theta plus 180 degree equal to, that is nothing but cos of theta plus pi 180 equal to minus cos theta. That would that's why it is coming minus root 2EB divided by TB cos 2 pi FCT in the interval 0 to TB. So I can write in shortcut, that is summarize. I can summarize SI of t equal to root 2 EB divided by TB cos 2 pi FCT. This is your theta IT. Instead of 0 degree and 180 degree, I can write theta IT, where theta IT is nothing but I represents 1 and 2. If theta 1t means S1T. Okay, S1T means it is related to theta 1t. Okay, theta 1t, and similarly S2T related to theta 2t, and this is the for 0 degree, this is for 180 degree phase shift. Okay. Now this is the simple your BPSK transmitter. Okay, this is simple BPSK transmitter where a product modulator is there. Okay, and the product modulator, what is the function of the product modulator? It products the two incoming signals, that is your binary waveform, that is either in the form of root EB and minus root EB. These we have already seen in the previous classes. This how it is coming root EB and what indicates this root EB and minus root EB, and your basis function, that is a carrier signal, that is nothing but the phi 1t equal root 2 divided by TB cos 2 pi FCT, and these two signals will be multiplied. Okay, then at the output of the product motor we will get one binary PSK waveform. Okay, that it is nothing but the binary waveform, that is this is the binary waveform. So this is these are the input data stream, and this is the your carrier signal. So what is the BPSK BPSK output? BPSK output is nothing but your, for 1 this is your same carrier, and after it is transition from 1 to minus 1, it is the phase is also reversal. Okay, so you can see again for 1 to 2 this transition, again this is phase reversal, and see 2 to 4 this is, there is no change of bits, so there is no phase reversal. Now it is changing from at this point, it is changing, that's why at this point the phase is changing. I have already seen we have already seen in the previous slide. Okay, so here only one basis function is considered, which is given by your this one, there is phi 1t equal to root 2 by TB cos 2 pi FCT. Okay, this is the basis function, because only one basis function is required to modulate the signal. Okay, so I can write in terms of basis function s1t equal to your root eb phi 1t and s2t equal to minus root eb phi 1t, and both are in the interval of 0 to tb. So therefore BPSK is characterized by one dimensional signal because we have only one basis function, one dimensional signal space. Okay, one dimensional signal. So this is very important, with two message points. Okay, one dimensional but with two message points. We have already seen in BASK also. That type the coordinate points as follows. So in case of BASK, BFSK also we have calculated the coordinate points. Okay, so herein also how we can calculate the coordinate points, that is S11. Okay, so S11 is nothing but your message point 1, okay, bit 1 with your basis function phi 1t. So I can integrate S1t, integrate the multiplication of S1t and phi 1t in the interval 0 to tb. This is small p, okay, dt. So I know S1t is nothing but the root 2 eb divided tb cos 2 pi fct, and phi 1t I know root 2 by tb cos 2 pi fct dt. So after multiplication and some calculation, we will get the S11 equal to plus root eb. Similarly S21 this subscript shows that 2 is nothing but the your S2t, that is message point, and 1 indicates the your basis function. So you can observe this one are same because we have only one basis function. Okay, so S2t phi 1t, that is your S2t is nothing but your minus minus root 2 eb by tb cos 2 pi fct. Similarly multiplication, your phi 1t is root 2 by tb cos 2 pi fct, okay, dt. So it would be minus root eb. We have calculated in the previous lectures also. Okay, now we can see the signal space diagram. Okay, so we have only one decision line. Okay, you can see one dimensional signal space, that is one dimensional. Okay, and having two message points. You can see the one dimensional. Okay, and we have two message points, that is minus root eb and plus root eb. That is, this is message point 1, this is message point 2. Okay, and this is the decision boundary. Okay, if any signal is coming in this region or region 2, it would be considered as minus root eb, and if any signal point is coming in this region, that is region 1, after this region, okay, then it would be considered as root eb. Okay, so the message S1t is located at S11 plus root eb, and S2t is located at S21 minus root eb. Two regions Z1, Z2 corresponding to messages 1 and 0. Okay, so Z1 belongs to 1 and Z2 belongs to point 0. The distance between message points is here, the distance is nothing but your root eb minus root eb. Yeah, nothing but 2 root eb. Sorry. So this is your receiver. Okay, so here we have transmitted signal at the transmitter, that is SIT, and after passing through the channel, okay, we know that we have noise is added. So this noise is added, and the received signal is your x of t, that is your input signal Si of t, and your Wt, that is noise. Okay, so this is nothing but this is simple receiver, this is BPSK receiver, and we have already seen the product modulator followed by integrator, and this is the decision making device. Okay, so this is your input signal, this is your phi 1t, that is your coherently we are receiving the signal. So again we are using 5 1T whatever we are using at the transmitter section. Okay. So after that we will product these two, and we will pass through this integrator. Okay. And after integrating, the signal will again pass through a decision device, that is I will get this is x1t. If x1 is greater than 0, then I will consider as bit 1, and if x1 is less than 0, I will consider the bit is 0. Okay. And your this 0, that is threshold, this is nothing but the VTS, that we can put this threshold accordingly, but here we can see your threshold is nothing, this is minus root TB, this is plus root TB, this would be middle point is 0. Okay. That is why this is the 0 threshold. Okay. Similarly, we can calculate the error performance of the BPSK signal. So likewise BASK and BFSK, here also we can see how we can analyze the error performance of BPSK signal. Okay. So let x sub t be the received signal, which is given by x sub t equal to SI of t plus WT. So I know that SIT is nothing but that your S1T and S2T. Okay. So your S1T is what is the S1T? That is nothing but root EB phi 1T. Okay. S1T equal to root EB phi 1T. But here, as we are considering the noise effect, that's why we have root EB phi 1T plus we have noise. Okay. This is the S1T for symbol 1. And similarly for symbol 0, it is S2T and minus root EB phi 1T plus WT. Okay. So let us assume that the symbol 0 is transmitted, the output we are considering the symbol 0 is transmitting. Okay. So symbol 0 means S2T is transmitting. Okay. So the output of the correlator is given by your integration 0 to TB, your signal x sub t. Okay. That is input signal x sub t. Okay. That is input signal x sub t multiplied by, this is the integrator, what will be the input, this is the input. This input is nothing but the product of these two. Okay. That is x sub t is your S2T plus WT, and this is the phi 1T. Okay. So this is S2T plus WT into phi 1T. I can split like this, integration 0 to TB. Okay. S2T phi 1T dt and 0 to TB WT phi 1T dt. So we can get S2T phi 1, I can write S21 and plus this is the noise, and whatever the operation is applied on the noise, it would be again one new noise, that is your W1. So S21 we know that is minus root TB, and your x1 is we have already know that is minus root TB plus some noise. So W1 is the random variable having Gaussian distribution. Your W1 is nothing but noise, it is having Gaussian distribution with your mean 0 and your variance equal to n naught by 2. Okay. This is n naught by 2. Okay. N naught by 2. Okay. Sigma square, that is variance, that is sigma is nothing but the standard deviation. Okay. Now the expected value of the random variable x1 is given by, so what is wherever the random variable concept is coming, first we are calculating the your expected value or mean and your variance of that particular random variable. So here your random variable expected value of the random variable, that is E of x1 is nothing but your what is the x1, your minus root TB plus W1. So expectation of minus root TB plus W1. that equal to minus expectation operation, it will come outside the expectation operation, and root TB your constant, that is root TB. And what is the expected value of W1? Because this is the mean. What is the, this is the noise, okay, noise mean. Here we can see the expected value of minus root EB plus expected value of W1, okay. So this is the minus root EB, and how it is coming 0? Because expected value of W1 is nothing but your mean of W1. So what is the mean of W1? That is 0, okay. So minus root EB plus 0, that is minus root EB. Similarly, the variance is nothing but the variance of x1 equal to variance of same minus root EB plus W1. So what is the variance of root EB? Sorry, so as it is constant, there is no variance, that's why it is 0. And but W1 has a variance of n naught by 2. So this is the variance n naught by 2. So after adding this, we will get the variance as total variance of x1 is n naught by 2. Now the conditional PDF of random variable x1 when symbol 0 is transmitted, we are analyzing the when symbol 0 is transmitting, is given by your fx1 and PDF of x1 when 0 is transmitted. So we know the PDF, this is the PDF, okay. 1 by root 2 pi sigma square is nothing but your n naught by 2. So 2 is cancelled, pi n naught, expectation of minus your x, instead of x I will write x1, okay. So plus root EB square divided by n naught. So when 0 is transmitted, an error will occur if x1 is greater than 0, in which case a decision is made in favor of 1 and therefore error occurs, okay. If x1 is greater than 0, then I will consider as 1, that's why this will be occur. So probability of error getting 0 is probability of x1 greater than 0 when symbol 0 is transmitted. So probability of error when 0 is transmitted can be computed by integrating the conditional PDF, okay. We will get the probability of error when transmitting the 0. So after integrating, I can see I have the PDF, this one, and after integrating I will get the like this value, and same following the same integration steps in the previous lecture we will get. So we will get this P naught equal to 1 by root pi integration root EB by naught infinite expectation of minus u square du, okay. We have already calculated this type of integrations before the before lectures, okay. So P of naught, I can find out the P naught equal to half ERFC root EB by n naught, okay. So similarly, the probability of error corresponding to symbol 1 is nothing but the, I will get for 0, this is the symbol 1 and the same probability of error. So the average is average probability of error for binary PSK is half into P of 0 plus P of 1, that is again same. So in case of here we are getting this much of probability of error. Now the average probability of error for binary FSK is nothing but we have already calculated, that root EB by 2 n naught, okay. Similarly, the average probability of error for coherent binary ASK is nothing but your probability of error equal to half ERFC. So root over ERFC of root over of EB by 4 n naught. You can see that there is you can remember also. So EB by n naught is only here EB by 2 n naught and here EB by 4 n naught, okay. So till now we have calculated the probability of error for BASK, BFSK, and now we have calculated for BPSK. So we have summarized how these probability of errors are coming and using random value analysis. So these are the references we have already seen in the every lecture. So this is the modern digital and analog communication system, BPLRT, and this is the digital communication for John J. Prokis. Okay. So in the next class we will see the another format of PSK, that is your DPSK. Okay. So that is your differential phase shift keying, and thank you very much.